Hi folks, we're going to take a look at number 12 from page 133. So what the question asks is, are any of these lines given here on the right parallel to this plane? And if so, do any of them actually lie on the plane? Okay, so here let's draw ourselves a little picture to make sure we understand this question. So say we've got a plane. Now if a line is parallel to a plane, certainly one option is that it could actually lie on the plane. Of course, it could lie above or below the plane, but still be parallel. Okay, so the question is, how can we tell this? And I think it's not going to be a big surprise that we're going to use the normal vector, because the normal vector, let me draw a really big normal vector here, to the plane. Okay, if the line is on the plane, will be perpendicular to it, and even if the line is not on the plane but parallel to it, should also be perpendicular to the normal vector. Okay, so that's going to be the first step for each of these lines, is see if the direction vector of the line is perpendicular to the normal. Okay, so let's start with A. So here we've got the normal vectors 4, 1, negative 1, and I'll dot that with the direction vector of the first. So here we've got 1, negative 2, 2. And here we've got 4 minus 2 minus 2, which is equal to 0. Okay, so that means the line is parallel to plane. Okay, now how would we tell that it's actually on the plane? So here, when we think of a line that would be parallel to this plane but not on it, we see that it won't share any points in common. Whereas if the line is actually on the plane, they must share all points. Okay, so similar to what we did to show that two lines were either parallel and distinct or parallel and coincident, we're going to do the same thing. We need to show that at least one point on the line also lies on the plane, or show that at least one point on the line does not appear on the plane. Okay, so let's start with the first one here. So here we've got the point 302, which is on the line, and I want to see whether that point is going to be on the plane. So it's just a matter of inputting it into the equation and see if the equation is satisfied. So here we've got 4 times 3 plus 0 minus 2 minus 10. And what do we have here? We have 12 minus 2 is 10 minus 10 is 0, meaning the equation is satisfied. So that means the line must be on the plane. Okay, as soon as they're parallel and they share one point in common, means they must share all points in common. Okay, so let's look at part B. Okay, so again here I'm going to take the normal vector to the plane, 4, 1, negative 1, and I'll dot it with the direction vector of the second line. So we see that that's going to be negative 3, 2, and negative 10. Okay. So we do this here, and what do we get? We get negative 12 plus 2 plus 10, and that's equal to 0. So that means the line is parallel to the plane. Now let's see if it's actually on the plane. So here we see that a point on this second line would be, well, 0, negative 5 is 0. Okay, so 0, negative 5, 0. And let's input that into the equation of the plane. So here, 4x plus y minus z minus 10. So 4 times 0 plus negative 5 minus 0 minus 10. And when we calculate that, what do we get? We get negative 5 minus 10 is negative 15, which is not equal to 0, meaning it does not satisfy the equation of the plane. So here, the line is parallel to the plane, but not on it. Okay, now let's check the last one, C. Okay, so again, we'll take the normal vector to the plane and dot it with the direction vector for this line here, which would be 4, negative 1, 1. So dot that with 4, negative 1, 1. And this is not looking too good here, because here we got 16 minus 1 minus 1, and that's clearly not equal to 0. Okay, so here the line is not parallel to the plane. And we don't even have to go any further, because if it's not parallel to the plane, there's no way that the line can actually be on the plane. Okay, so that's the solution to this problem here.